Now that we have knowledge about entropy and the second law of thermodynamics, I want to revisit the concept of heat engines so that we could have a more quantitative discussion about them. And so heat engines, once again, they convert heat into work. But for any real-life process, the heat engines, or another thing to call them, you think of them as a power plant. A heat engine or a power plant, they don't convert 100% of the heat that goes into them into work. Some of that heat has to be lost to what we call a cold reservoir. Okay? All right, and so when we're modeling or describing heat engines, we could draw them like this. And so with a heat engine, the input heat is going to come from some sort of heat reservoir. Right? That heat reservoir is going to give off a flow rate of heat, which I'll call QH dot, at some temperature, hot. Okay? This heat then goes into our engine. Which is going to convert some of that input heat, QH, into work. But as I mentioned, not all of the heat gets turned into work. And so some of that heat is then exerted or given off by the system as a cold heat, if you will. And that enters into a cold reservoir that's at a temperature Tc. Okay? Alright, and so that's the basic concept of a heat engine. But typically, at least the stuff that goes on inside the engine, it's not a single step process. There's actually multiple steps that are involved in order to turn the heat into work. But essentially, all these steps will operate in a cycle. So heat engines operate in cycles where the engine will start at some initial state. It'll then go through all these steps in order to turn the heat into work. And then after a cycle is completed, that engine will then be back at that initial state. And so because engines operate in cycles, so the state of the engine and when I refer to state, I'm emphasizing the state variables, so things like temperature, pressure, and volume of engine is the same at the end of cycle. Okay? And so because the engine returns back to its initial conditions, that means that if we consider the overall system of the engine, if we take a look at how its internal energy, it's the derivative of its internal energy, derivative of its enthalpy, or its derivative of its entropy, if we consider the entire engine cycle, all of these things will be equal to 0, right, as the engine completes its entire cycle. And the reason for that is, once again, these things are state variables. And so if the end conditions are the same as the beginning conditions, that means that the internal energy, enthalpy, and entropy are also going to be the same. Hence, the derivatives will be 0. Okay? Alright, in any case, so with heat engines, they need to have a cold reservoir. Because if they didn't have a cold reservoir, that would violate the second law of thermodynamics. Alright, and I could show you a quick example here. If we start with the entropy balance of just a generic heat engine, and so I'll write it in the rate form, so ds dt, and then is going to be equal to the summation of the different heat rates going into the system plus Sgen. Okay. For a generic heat engine, we have two different types of heat. We have QH going in and QC going out. All right. And so I'll write these here, QH over T going in. And I'm writing plus here because I'm just adding up the heats. But what we do know is that based on the direction of the arrows in the diagram, we know that this one is going to be positive and this one is going to be negative, less than 0. Okay, so that's built into the variable itself. Okay. All right. In any case, so we have that, and we know that since an engine operates in a cycle, ds dt is going to be equal to 0. All right. Okay, so we have this is equal to 0. All right, and so in the case that QC was equal to 0, if we said that there was no cold reservoir, what we would get would be that 0 is equal to QH divided by TH. Oh, it should be TH and TC over here. So 0 is equal to QH over TH plus Sgen. So if we solve for Sgen, we get that Sgen is equal to negative QH over TH. But like I said up here, QH is going into the system, so it's positive. So negative QH would then give us a negative number. And as we know from the second law of thermodynamics, the entropy generated in the system can't be negative. Right? And so what this tells us is if we did not have a cold reservoir, what we would get is a physically impossible process. Okay? And so that tells us, therefore, QC cannot be equal to 0.